computer. Okay. Share screen, Mars. So I explained already 5.1, 5.2, but let's start in the middle of 5.2 here. And let's start. I explained a little bit how you're going to do it. We have this code 31. What am I doing? Oh, cancel. I want to do new. It's hard to talk in new. And I'm not going to worry about the syscalls. You'll worry about that. You know how to do syscalls, get numbers. But let's say I've got the number. So how am I going to get to check the most significant bits? Essentially, I've got a number that's something like, 0x, A, B, C, D, F, F, B, B. Okay? Let's say that's a number, right? He typed in a number and I got it. I want to just look at the first byte, which is AB. How am I going to look at? I want to see if that part of it is equal to 31. Right? That's what the question said. If it's equal to 31, then do something. We'll worry about the do something in a minute, but in a few minutes. But first, let's worry about how to even find out if it's 31 or some other number. How am I going to find that out? Anyone have a suggestion?
Do you store it in a different register and then shift right?
Oh, very good. Store it in another register so I don't ruin the number, and then shift it right. How many do I have to shift it right? I got to shift it right this amount. I got to push all of those into the bottomless pit on the right. So that'll make my number smaller. How much do I have to shift it? Well, each of this is 2. Each 2 is a byte. I got to do 3 bytes, 24 bits. So 24. I got to shift by 24. Now, the way you do that is, well, first of all, we're going to do something like this. Li into register T0. You can just write like that, the value 31, because I want to compare it to that. And now, let's say that this number is in, A0. Let's say, truth is, you're not allowed to. The truth is, this is how you really can't do this, right? It'll work, it'll compile, but remember, Li is really just add-I, and add-I only allows a 16-bit number, and this is more than 16 bits. This is 32 bits. So the compiler will convert it in a certain way. Actually, I should explain how to do that. Let's compile this. Okay, so let's compile this. So what did it do? It turned it into a Louis and an Ori. What it really did, this is a little bit, now let's change it into a Louis and Ori ourselves. Now, what does it mean, a Louis? Louis is load upper immediate. So, for example, I can do like this. The upper part, I want to put A, B, C, E into A0. How would I do this? This is a parenthetical little excursion I'm explaining here. how you could put a larger number than 16 bits into a register. So if you do like this, the special command load upper immediate, which says take this number and stick it into A0, but not in the A0, the 16 rightmost bits, put it in the 16 leftmost bits. So now I've filled in part of what I wanted to fill in, and now I just have to put in the other part into the lower part. So for that, I do an OR operation, or immediate $A0 is going to be the OR of $A0, and I'm going to OR that bitwise OR with 0x FFBB. That's what I wanted to put there.
Is this what we're supposed to do? What you said? I'm a little confused about what.
No, this is parenthetical. I wanted to explain to you something that I usually explain to the students.
We could use the li for it.
You're not going to need to, because you're going to get it from the user, right? The number is going to come in from the user. I'm just explaining something. I'm just teaching you something.
Oh, okay.
That I'm just teaching you something that's completely unnecessary, but it's, as I say, a parenthetical remark here. It's completely unnecessary, but I want you to know it because it might be on the exam, on the quiz. You should know the command load upper immediate and what purpose it has. In other words, in my slides, I actually talk about it, but I'm just going to do it now for you because I didn't talk about it before. Load upper immediate is going to put the here. Let's see how it works. Make that as a comment. Compile. Notice now it changes. It doesn't change anything. Load upper. Now I run it, and where did I put it into? I put it into 4. Let's look over at 4 here. Register 4. Look at it has A, B, C. What did I write? A, B, C, E. I don't know my alphabet. You see that says it's very small, but it says A, B, C, E. And notice it's on the most significant bits. It's on the left side. And I want to put A, B, C, E, and then F, F, B, B. So I did the first part. And how am I going to do the second part? Well, first I'll show you that works, and then I'll explain why. Compile. Notice it didn't change anything. It took it exactly. I mean, it added these zeros here. I don't know why. That doesn't matter. And now look. A, B, C, F, F, B, B. I did it in 2 steps. Now, the second step, why does that work? Because essentially, and this lesson is important for what we're going to do in the continuation, but A0 looks like, it's A0 is like this. It's some kind of set of 1s and 0s like that. And then the second half of it is a bunch of zeros. I'm just, I'm not trying to be exact. I'm just showing you the basic idea. That I put the A, this is the A, B, C, E, for example. And this is the zeros that are still there. Now, when I do an OR with it, I do like this. I do, Control Z. If I do OR, a logical OR here, and I put with number, 0, 0, 0, 0, 0, and then whatever FBB is, something like this. I don't know, something like that. So what's going to happen is when I do OR, the zeros here are going to have no effect. All the 1s will become 1s down here, and all the zeros will remain zeros. And when I do and all these zeros will have no effect. So I'm essentially scrunching the 2 numbers together, and I have the left side and the right side all together. That's how you can do something that you might have thought was impossible, which is load into a register all 32 bits. Because your normal add I, which is all you up to now really have, can only take, a register, and then 16 bits, not 32 bits. So this is the method for putting in the whole 32-bit number if you wanted to. Okay, so, but again, like I said, this is not necessary for this targil, but it's something necessary for you to know. In this targil, he'll give you the number and you'll just have it stored. He'll type in a decimal number and it'll be stored in binary, and you'll want to compare it to 31. How are you going to compare it to 31?
How do we, you were talking about shifting it? What's the command?
Yeah, so
for
now
shifting?
back to where we were. Shift right. So you got this number and you want it, your number is essentially, let's just put it back like this. Your number looks like something like that. And you want to shift it right. So there's a command called shift right logical. There's two shift rights. There's shift right arithmetic and shift right logical. Shift right logical means shift it and fill in zeros on the left side. So the number, if you did shift right logical of, let's say, into T1, move A0 24 places. So now, if I looked at T1, it would look like this. It would look like 24 places. I shifted it right. So it would be like 24 zeros, 1, 2, 3, no, not 24. Let's write in hex. So 0x, 0x, 24 zeros divided by 4 is 6 zeros. 1, 2, 3, 4, 5, 6. And then my AB. Because I shifted everything right and it filled it in with zeros. Now, there is a shift right arithmetic, but you don't want to use that. What is the difference? Shift right arithmetic looks at the number and says, if this is a positive number, then do the same thing as you did before. But if this is a negative number, then don't put zeros here in all these, put ones there to maintain the negativity of the number. And therefore, it's only logical to do that in arithmetic. That's why it's called shift right arithmetic. It's only when you're
Can you
doing.
explain that again, please? How the shift right arithmetic works?
Yeah, shift right arithmetic, right? I'm sort of filling in a couple gaps in things that we didn't learn. We didn't learn about this command, and you need to know it also. Shift right arithmetic means move it right, but let's say, look, let's take this number for example. What is A? How do you write A? A is what? Is 10. Sorry, A is 10, yeah. So how do you write 10 by
0, 1, 0?
It would be 1, 0, 1, 0, exactly. That's A. Now, that means if you look at this number, if I asked you, is this number positive or negative? What would you say in 2's complement?
It's negative.
Negative.
It's a negative number. If I did the regular shift right logical, it would become this number, right? 0, 0, 0, 0, AB. Is that positive or negative?
It's positive.
It's positive.
So why?
Now, if
So
I
we
did
should
the
be
shift,
using.
wait a second. So if I am doing the shift simply because I want to divide the number by 2 to the 24th, and I say, oh, I want to divide this number by 2 to the 24th, and the fastest way to do that is to shift it right 24 spaces. So I'll just shift it right. All of a sudden, I'll get a positive number when it should have been a negative number because it was a negative number to begin with. So in order to prevent that and maintain the sign of whatever the number is, we have shift right arithmetic, which checks what the sign is. And if it was started with a 1, it leaves a 1. So this will all be, so it'll actually be the number FF, 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 AB. That's what shift right arithmetic would do. It would put 1s in there. In other words, it would do what we called sign extension of the number. It would or I would call it maintaining the sign of whatever the number was. But that's only relevant when we're doing math operations. Like we actually want to divide a actual integer value by 22 to the 24th. But we don't want to do that here. We just want to mama shift it and get 0. We definitely want to have zeros there because we want to change. We want to ignore those digits, but look at, and we're really just looking at digits. You know, zeros and ones. We don't care about it's not, this number doesn't represent a value. It's just a set of ones and zeros for us. So we're going to do shift right logical and get. Now, if the number was positive, it would not be any different, right? But we don't know that it's going to be positive or negative, so we have to do shift right logical to guarantee us that we get zeros. So now we got zeros. Now we got zeros over here. And we still don't know what our number is. We did our shift, but we want to compare it to 31. Is it 31?
Just BEQ with T0 now?
Yeah. So now it's easy. So we just do
BNE.
BEQ $T0 $T1. And if they're equal, then jump to location code 31, for example. And then at code 31, we'll do something. And similarly, we'll check it. We'll do BEQ. $T2, $T1, code 78. If you remember, there was a 78 here. Stop new share. Right, we wanted to check if it's 31, 30, 48, 74. So it's not 78, but 30, for example. So we'll have to do code 30, and we'll have to load 30 into a different register. Yeah, etc. For all 4 codes, I'll have to load them all up, and I'll have to check. I'll have to do my shift, and then see if it's equal. Is it so far so good?
Yep.
Okay.
I have a question about the hexadecimal notation, just because I don't know if I've had so much practice with it. How do you
Yeah.
store a negative number in hex, like 0x and then a negative number?
Well, there's no meaning to that. In other words, maybe you could. Yeah, I guess you could write what you're gonna write like this is negative. I don't know if it works like that.
Is that like, is there a way to have a negative
No,
number?
it
in
doesn't
hex?
really mean anything. No, because when you're referring to numbers as binary values, then you're just talking about ones and zeros. So, there's no such thing as negative. Maybe there is. I mean, maybe you could write negative. I never
Isn't it
tried.
used for offsets?
Let's see.
specifically? Like offsets for memory addresses.
Yeah, but
So
how
we
would you
don't-
even notate it? I don't know how
For
you
the
would note it.
0x, like negative 0x31, then
Oh yeah, you've done
other
that?
base address. I don't think I've seen it in MIPS, but I've seen it in other assembly code I've worked with.
Okay, I'm not familiar. I'm not, I don't know everything, even about what I teach. Because I teach too many different subjects. You can ask the guys in Shana Gimel. I teach too many different subjects. Okay, so yeah, it accepted that. So look what it does. It puts ones in front of it.
So that's the notation. I mean, could you also theoretically, like what you said, meaning when it translates the command, let's say, like the LUI and the ORI, so could you put in, like, let's say you had a number a 16-bit number that started with a 1, and you LUI'd it to the beginning, then would it end up being negative because it's going to start with a 1, even though you hadn't necessarily?
Yes. In other words, LUI is, if you put it negative. You see, that's an interesting question. Like, let's think of a number that's, That's an interesting question.
There,
LUI,
I mean, there is no number that's like 16 bits and it takes up the, well, actually, oh, never mind. I'm saying like 17, let's say, if you put in 17, then isn't that,
Here,
wouldn't that
wait a
start with a
second.
one?
here, look at this number, 31FF. What does it start with? 3, it starts with 3. 3 is 0011. So this number by its nature is a positive number, right? 0. But if I put a negative in front of it, let's see what it does. It doesn't like that. Okay, I'm glad.
How is that out of range exactly? What's the explanation of that?
Well, I don't know. What if I made it even smaller? What if I change? Wait, what if I do like this? Still out of range. It's because, I mean, I would just say logically, it's silly what you're trying to do here. When you're using load up or immediate, you're trying to, you're really dealing with unsigned numbers. You're saying, I'm take these bits and shove them into the left side. So
Then doesn't negative 31, negative hexadecimal 31 have a
it exists,
binary
you're saying.
representation?
You're saying
Yeah,
it
so why doesn't it
exists.
just take that number and put it in, like, I mean, I don't know what it is. Probably like one, whatever it is, but shouldn't it just take those bits and put them into the upper 16 bit?
Let's see what it is.
The assembler is probably first converting the negative literal into a 16-bit number, and then seeing that into a 32-bit number, then seeing that the first 16 bits aren't zeros, and saying it's out of bounds.
Right, you see, well, wait a second. Converted it into, well, what is that what I wrote? Is that right? No, here, the third one. Second one. Here, let's get rid of this.
The LI we said works, but the LUI doesn't work.
Yeah, I want to see again what it does though. Right, it converted it. Look, it already converted it to these Fs. Although I don't quite understand. Right, really, see, this is one thing that bothers me. I don't understand why. If add IU, add I we know, U just means unsigned. But how come it's got 32 bits here? Shouldn't it be just 16 bits? It can't be more than 30. It can only be 16 bits. You see over here, it's just FFCF. It's just 32 bits. It's just 16 bits because the coding can't allow that.
And it's only going to save those. Wait, but when it puts it into the register, doesn't it fill up the first 16 bits with the Fs to make it negative?
Yeah, it will. It will. That'll be but that will be the job of the assembler of the machine. In other words, here, I don't know, FF. Let's see what this does. Now it looks a little bit better. No. So what did it do? Look what it did. It changed it to CE01 because that's how you represent that number in 2's complement. So it's like, I don't know who said that before. The assembler first changes it. And what's going on here is that it's taking this negative number. It's just like I wrote negative 25. And it's converting it into the 2's complement version in binary. And it gets all these Fs. Then it does the add where it ignores the first 4 Fs and just says the CE01. That's the actual encoding.
Why is it ignoring the first 4 Fs?
Because it has to, because the add I only has 16 places to put a number.
But what does it do with the first 16 bits of the number? If it's negative, it leaves them as 0? Meaning the upper 16 bits of the register will still be
well,
zeros.
let's run
and not
this.
Fs.
Let's see what value will be there.
For the whole FFFFFFCE01 in E0.
Wait, I want to see what 8 is. It did get there. The F's got there.
So it
But in the
sign
code-
extends the 16-bit number to 32 bits and puts that into the
Oh,
register.
right, and the C,
Then-
and notice it changed it to a C from what we wrote. We wrote a 31 where Idafka wanted a 0 there, but when it became negative, it changed it to a C. C is 12, so C starts with a 1. Right? It's a 1, 1, 0, 0. So it'll sign extend it, exactly. That's but like I said, the machine will do that. The ma'abed, the processor will take that number and sign extend it and then and then add it. That's the job of the processor. That's what you learned about when you're learning with Avi about how the actual processor does its job. It has that sign extension module machine.
So what Benji was saying for the LUI, why it didn't work is because it'll sign extend the number and then try and put it into the first 16 bits. Saying like why, and I guess I'm asking Benji for the explanation. But why exactly, meaning if it's a positive number and it's all zeros when it sign extends it, why does that get to go into the first 16 bits? But if you sign extend it to be negative, and if it's negative and you sign extend it to be all F's, why does that not go into the number, into the first 16 bits, I mean?
You're saying
The error on the bottom, why exactly is a negative number out of range for the first 16 bits of the number and a positive number wouldn't be out of range? If it's just gonna take the 16 bits, whatever they are, and put them there.
I would say it's like this. This is my answer. You can take it or leave it. But maybe Benji has a better answer. But my answer is that the hardware is not built when you're using a load upper immediately that doesn't. Oh, I see what you're saying. You're saying, why doesn't it just change this to whatever it was over there? What was it? C, C1, A, B, I don't know, whatever it was. Why doesn't it just change it to that and take away the sign and then everything would work?
Yeah,
In other words, like I can get it to work. What was it? What was the number? It was
31 FF. Maybe do
31
an LI
FF with a
31
negative.
FF and then
So let's just
do LUI.
and then do
with,
LI
C-
and see what we get. No, see what we get. And we get, it changes it to CE01. So now I can just write CE01 and get rid of the minus and it'll work.
Yeah, exactly. That's the question.
And why wasn't but here you notice that it was zeros there.
I mean, it sounds like when you do an LUI, you basically have to give it a positive number. Even if
Oh,
you're
sorry. No,
technically
now I'm
giving
sorry.
it a
Now it'll work
negative
when I do
number,
this.
it'll
I'm sorry, when I
assume
do
it's
this.
positive.
I had to do it like that. Now it'll work. Load upper immediate with that number and it'll just put it in. Why does it work? I guess, here's my answer. Because what's the difference between this one and what we saw before? The zeros here, right? In other words, when we did it,
Meaning
when we
load
did
immediate.
the
These are all
load,
unsigned.
the load
basically.
immediate was 0x FFFFC01. In other words, it put F's there. And the simulator knew to convert that and to chop off those F's. But the simulator is built in such a way that a LUI, it doesn't, it needs to have zeros here. You see how it converted to zeros? It needs to have zeros here. Or I put it another way, the load upper immediate is just a binary processor. In other words,
I mean, wait, is it because it's unsigned? I mean, does an unsigned command not allow you to put a negative symbol? Is that maybe the explanation?
You could say it like that. It is let's say it's a binary command. It's an unsigned command. Yes. And therefore it requires zeros in the bits that it's not using. In other words, I'm just saying it's kind of weird that there are zeros here at all. Why wouldn't the command be LUI? Oh, because LUI 8, and then 0x CE01. Why are these zeros getting put in there? Anyway, the load upper immediate is just going to take the right side and put it in the top. It's going to ignore these bits. So why are they there at all? And why is it so? I don't quite see why it's done like that. I mean, what Benji said, the one word he said was the simulator doesn't allow it. You know,
I think just a
that's all.
quirk of the assembler. It's not
What?
nothing to do with the processor itself, just how the assembler
Right.
is built.
Something about the assembler, right? Anyway, it should work. If I can do that, then I should be able to write what I had before. It's just that the assembler. But notice that writing this is not really acceptable, because that's also like the assembler has to change that. In other words, writing whatever I had before. What was it? Oh, by the way, oh, wait, I'm thinking about it now. Now I understand something. Wait, I think I understand something better now. Sorry to be learning with you guys while we're going. This probably loses a lot of you. Now I understand why it's out of range. I understand why it's out of range. Because when we wrote, oh no, wait, AB. No, we wrote AB. Yeah, I don't know. I don't know. I don't know. I don't know exactly why. It's just something. It should, there's something about the assembler, but it's nothing to do with the language. Nothing to do with the actual machine. All right, anyway, enough of that. Load upper immediate. We learned how we can do the shift right on the number. And here, let's put back the number. We put our number in A0. We shift right. We can add 31. We can do LI $T1 0x 31. So if it's T1, we'll jump there, we'll jump there. Now, let's go back to the question. Now it'll compile. No, it doesn't compile because 31 is not existent, but I have to write,
You need to call in.
And now it'll compile. Fine. So that's the basic beginning. Now let's go back to the question. So if it's 31, then the program should place a 1 in the following bits, 0, 1, 6, 7. How are you going to do that? You got to put in those bits. So 0, 1, 6, 7.
Can you OR it with the binary representation of whatever, meaning the number that's 32 bits and you have a zeros everywhere except for ones in 0, 1, 6, 7?
Yes, I'm going to show you exactly that. Okay, so yes, exactly what you said. We're going to take the number. Oh, let me just move this. We're going to take the number, and let's say the number. Well, first I want to show you. Let's say the number was something like this: a lot of ones, a lot of zeros, a lot of ones, and then the last 8 bits were 1, 0, 1, 0, 1, 0, 1, 0. Did I get enough there? Yeah. So what I want to do is I want to put in the first and in 0 and 1 I want to put a 1, and in 6 and 7 I want to put 1. So how do I do that? So there's something called an OR. OR operation. What I do is I put a lot of zeros here, and then over here where I want it to be a 1, I just put a 1, and where I don't want to affect it, I'll put zeros. So now what's gonna happen? The OR is it's a bitwise OR. That means it checks every bit one by one. That's what this OR operation does. So it checks 1 and 1, and it's gonna put a 1 underneath here. It's gonna put a 1, 1, 1, 1, 1. And now they're both 0, so it's gonna put 0, 0, 0, 0. And now 1, 1. It's just gonna copy, so it doesn't have any effect. But all of a sudden, when I get over here, it's gonna have an effect. The 1 will obviously remain a 1, but now 0, 1 will become 1. Now here with the zeros has no effect, so it's gonna remain 1, 0, 1, 0. And then the 1, 1. So now I've effectively forced it to be a 1 at the locations that he told me, 6, 7, and 0 and 1, with an OR. Derech Agav, you have in C++ the same operator. You could do like this: int a equals b or c. And that's the OR operator. It's a bitwise OR operator in C++. And it'll do the same process. It'll check the bits of the numbers, just so you understand that it exists in C++ also. That's what I'm going to do. So I'm going to have to OR it, but I have to create this mask. We call this a mask. I have to create this mask. Well, it's pretty easy to create because all I have to do is, know this value. What is this value? I don't know, 100 and, what is it, 64. No,
You
that's
could just save the hexadecimal representation.
exactly much easier to just save their hexadecimal. So I can do like this: $, LI, $S0 is equal to the hexadecimal value.
Can't you use 0b? You just write down a binary.
What C3? What'd you say? I could
You could
convert
probably
it.
just do 0b instead of x. No, say, but and write it in binary, which would just make it
Yeah,
easier
I
to
could do
read. See what's
0b,
going on.
but I like it's not so hard to convert to hex. This is C because it's 12, and this is 3. So C3. And then I'll just do OR. And I want to change the number. So the number that I got, let's say, is in A0. So I'll do OR $A0, $A0, and then $S0.
There's also an OR immediate, at least according to the green card.
Yes, I can do OR immediate also. Either way. Yes, I can do OR immediate and put that number there. So that's easy. How are you? There's another one that says, if you look at the question, if the 30, put a 0, how are you going to put zeros there? The OR is not going to help you.
You put an and, just with everything else being 1 instead of 0, and that being 0.
What? What'd you say? Do an OR
An
also?
and. No.
No, an and is not going to
Do
help.
an and.
We do an and. We want to turn them to 0. So if you do an and with a 0 at that position and everywhere else a 1, then the 1s are going to remain 1s. But the places that I put zeros, it'll automatically turn to a 0, right? How are you going to do? How are you going to invert the bits? Here it says invert the bits. That means if it was a 1, it should be a 0, and a 0 should be a 1. What should do that?
Is there an XOR command? Maybe.
There is. There is.
Perfect. Let's use that.
So you go, it's like this. XOR, or exclusive OR. By the way, in C++, there's this symbol for exclusive OR. So exclusive OR, let's see how that's gonna work. If I wanna flip the bits. So I do this. I think I pretty much do this. The exclusive OR will not affect the ones. The ones will still be, and they won't affect the zeros. But if I put a 1 here with exclusive OR, now 1 and 1 becomes 0.
But how do you know what the bits are for 8 through 15? I mean, you have to invert them no
I just have
matter
to make my mask.
whatever.
I just have to make my mask correctly. That's my mask. And then I take the number and I apply my mask to it with a XOR. Now my mask is 11000011. So these two bits will now become 0, 1. These bits will not change. And these bits will become, well, 1 and 1 in exclusive OR is 0, and 0 and 1 is 1. So I flip the bits.
So XORing with all ones, meaning XORing any sequence with ones will give you the inverse, will flip the bits of
Yes,
the original
XOR with
sequence.
0 will have no effect, and XOR with 1 will flip the bit. That's just the quality of that. That's always true. Now, with the last one, the last thing to do is if it's 74, then the program should the program should perform shift left n places. The n is equal to the value of bits 24 to 25. So we're going to do we're going to shift the number left by however many places is indicated by bits 21 to 24. So
You have to use a mask to get the value of the bits 20 to 24 with
how are you going to
zeros
get
and
the value of those bits? Let's
with
say,
an OR with one.
you know, I want these bits, let's say. I don't know. What am I going to do? I could, there's two ways. There's one way to do it with masks is to first blank out these numbers. How do you blank out these numbers? Turn them all to zeros. How do I do that? By having a mask here with doing a zeros here and doing an and. I do an and, I'll put zeros here, and then I'll put ones over here where I want to preserve it, and zeros over here. Now I've gotten rid of everything. The only problem is my number is way too big because it's over here. It's over, there's zeros over here. I got to get rid of these zeros so I know what the number is. I got to look at that number on its own. So the way to do that is to shift it to the right and get rid of all these things. But a simpler way, and one of my students came up with it, I didn't, which is shift it left first, this many places. First shift it left this many places. Now all those numbers will go away into the bottomless pit. Now shift it right this number of places plus this number of places. In other words, now this number that I wanted to keep, let's say I want to keep this number, it's all the way over on the right here. So now shift it all the way back to the beginning. So I did 2 shifts and I got rid of everything that I didn't want, right? Pushed it off one way. It's like you have a big salami. You chop off the right end, chop off the left end, you get the middle. So that's it. Any questions? All right, so I'll stop the recording.